Okay, let's get started. Good afternoon, everyone. My name is Zhen Zhang. I am from Arizona State University, and I want to thank Guan and Mo for this opportunity to talk with you and discuss with you about using meta-analysis to inform the robustness of empirical research findings. So, an outline for today. I know we have limited time, so I will try to meet the goal of finishing within 45 minutes, and please hold out the questions toward the end if you have any. I'm sure you have many questions. So the outline, I'll first review the different effect size measures in the science of organizations, then briefly talk about how meta-analysis has been typically used and what are the indicators of effect size heterogeneity in meta-analysis. And then I will spend most of the time to talk about the two different ways of combining meta-analysis and structural equation modeling to allow researchers to test relationships or models that they have not tested, may or may not tested in their primary studies. Then I will summarize with recommendations for how to keep this in our toolbox for enhancing the interpretation and evaluation of primary study findings. So a quick review, many of you already know this. In terms of effect size measures, there are many different forms. And for a lot of the OBHR researchers, we care a lot about the correlation. So Pearson product moment correlation. Well, if you are doing experimental research, then the D statistics or even odds ratios may be your focus area. And R squares explain the variances, eta squares in ANOVA. Those are also effect size measures. And here I listed a question mark just after standardized regression coefficients, because that's something that is tricky in terms of if you compare standardized regression coefficients across different studies, you will need to have the same set of predictors and control variables in order to be able to compare across studies. So on the one hand, it's a measure of standardized effect size, but on the other hand, you need to have the same set of coefficients in order to be comparable across different studies. And there are many other different measures of effect sizes. Today we will be focusing on correlations, but the same logic could be applied to other like D statistics and others in terms of how to combine the meta-analysis method and to test a model that can allow you to do things above meta-analysis. A quick review: meta-analysis, following the tradition of Schmidt and Hunter, we define it as has been defined as the quantitatively summarize a body of work on a particular relationship. And as you will see in the next few slides, when you present the meta-analysis results, you typically have to report the average observed correlation, the standard deviation of it, and after you correct for the artifacts, then you can report the estimated true population correlation, which is called rho, and the standard deviation of it. One note here is that today we will be only talking about the conventional meta-analysis, where you will summarize research findings across independently conducted studies. We're not talking about the so-called internal or single paper meta-analysis, where you have one group of researchers having a few primary studies and doing the synthesize and analysis within the same paper and present the meta-analytical results in that one paper. So that's not the focus for today. So with the traditional or conventional meta-analysis, the heterogeneity of those effects can be indicated by a few different things. And for example, the standard deviation of the true population correlation, which is SD rho. And you can look at the width of the credibility intervals, which I will be defining very shortly. And also the percentage of observed variance that is accounted for by artifacts, so on and so forth. So some of the methods, some of the indicators had been popular in previous years, but now tend to fall off of favor by researchers. But the standard deviation of rho and also credibility intervals have been pretty robust in terms of have continued to be popular to be used by researchers. Here is an example of the meta-analysis table, which you can see in many published meta-analyses. So the reference is listed here at the bottom. So I would like to highlight a few things for you to think about. First of all, let's look at this line where it gives us the information that is corresponding to the column labels. So first number 32 means the number of independent samples. So one study could have multiple samples, so the K counts on samples. And as you see on the top at the label, we will be looking at the true population, estimated true population, and the standard deviation of it. Then there are two columns called the confidence interval boundaries, which is 95%, and the 80% credibility interval boundaries. So considering the time, I will not be going through the definitions, but on the other more of parameters or reported information. But I would like to highlight that in this line, the standard deviation of rho is estimated as a positive value. In contrast, if you look at the other highlighted area, standard deviation of rho is 0, which I will be explaining in the next slide in terms of what it really means statistically and conceptually. And as you'll see here, when the standard deviation of rho is 0.00, the credibility interval is like with the lower boundary and upper boundary is the same value, which means there's no variation between the two boundaries. Before we talk about why it could be 0 and what does that mean, I would like to explain a little bit on the technical side of those two intervals. So credibility intervals are based upon Bayesian logic. When it was first introduced by Schmidt and Hunter in their 1977 paper, they actually described why we have to look at the posterior distribution of the correlation after correcting for the artifacts and use that to construct the confidence intervals. And in terms of interpretation, if you have a wider CVs, that means there is a potential to have one moderator or multiple moderators on that relationship of focus. Whereas when you look at confidence intervals, it is estimating the accuracy of the mean observed correlation. And it is calculated with a similar formula, but just replacing the standard deviation of rho by the standard error of the estimated R. So for technical details, you can refer to Hunter and Schmidt's books, different versions of books for the technical details. But I want to emphasize that confidence intervals has, to some extent, an overemphasis on significance testing, whereas the credibility intervals can actually give you rich information in terms of how the actual observed or the actual true population is distributed across different values. So here is a slide to explain why the SD rho could be 0. And sometimes you may realize that by through your own work and reading others' publications, you may realize that sometimes the percentage of explained variance is greater than 100%. The reason was the calculation was based upon this equation. So the variance, the first equation there, the variance of sample correlations equals to the variance of population correlations plus the variance due to sampling error. And the sampling error, so basically this term, if you rearrange the terms, so the variance of rho equals variance of observed sample correlation minus the sampling error. And this term has a particular formula to calculate. When this value is greater than your observed variance, that gives you the bigger than 100% percentage. So in that situation, typically researchers will just fix the total sum or the difference between the two as 0 rather than going to a negative number. So now, understanding how, after we know how the CVs versus CIs are interpreted and calculated, let's look at the sources of heterogeneity when you meta-analyze primary studies. So there are two different types. The first type of heterogeneity may be due to moderators. Sometimes it's one moderator, sometimes there's a group of different moderators at work. And this source of heterogeneity and the ways to consider it is related to the general reliability of the primary study findings. So you can think of this as different subpopulations or even totally different populations. Looking at for example, 30 studies, 15 of them may come from a different culture, the other 15 may come from another culture. And the heterogeneity you identified when you meta-analyzing those 30 studies can actually give you the hint or give you the direction of to look at those potentially moderators from the cultural perspective, and also examine whether a particular study is generalizable, the findings from one culture is generalizable to other settings, other cultures. So that's why I say here it is related to generalizability. In contrast, heterogeneity, after considering the moderators, if it's likely that you'll still have some normal variations in the observed correlations, even if you considered already it's a homogeneous population. So in this aspect, it's more related to the replicability of primary study findings. So let's assume you already identify a homogeneous population or subpopulation, and you are doing a few primary studies out of that population. You still have variations, but this type of variation is no longer due to, let's assume, no longer due to any moderators. It's only due to the remaining sampling error you may have. And this is more relevant for replicability rather than due to additional moderators you have to consider before you're reaching this stage. So let's use one example to look at how we can actually combine our knowledge so far in terms of meta-analysis, heterogeneity, and testing a structural model. So this is a very simple model where you have variable x predicting two parallel mediators and then predicting the ultimate outcome variable y. So when you are able to combine meta-analysis results and structural equation modeling, researchers can actually test relationships that they have never tested before in any primary study. The reason is some of the studies may have tested the front part, but not the second part. And when you combine them together in a meta-analysis, you have actually the chance to test the whole model, assuming that primary studies have not tested it before. In addition to look at the single path coefficients, you can actually use the so-called meta-analytic SEM to test the mediation effect, for example, the upper path mediation effect, or the difference between the two mediation effects, or any other combination you want to test, as long as it has a conceptual meaning of it. So the first approach, when we come to the combination of meta-analysis and structural equation modeling, was proposed by Vaisvesvaran and Ons in 1995. It's called the meta-analytic SEM approach. So in this approach, as many of you already are familiar with, you construct a pairwise correlation matrix With that matrix, you can use as an input. Actually, for the matrix, you only need the information at the lower diagonal, because it will be repeating the same information on the upper diagonal. So when you have this information ready, then you can use that as an input matrix into any SEM software and do the testing as a second step. It's important to note that some of the cells may come from study set A, other cells may come from a different study set, and some cells the information here may come from prior meta-analyses. So that's a way to really synthesize and combine prior knowledge that may not, from studies that may not have been looking at the same mediation model as we are looking at here. So in this approach, a critique on this approach is the matrix, because it is constructed in a pairwise way. So the correlation between X to M1 is not taking into any consideration of the correlation between X with M2. So due to that reason, it's very likely that you will encounter some non-positively definite matrices. And in that situation, there's no way that you can run an SEM in the second step. We'll talk about that later in the slides when we talk about how to incorporate heterogeneity there. And again, it's an average correlation matrix, and heterogeneity is not often considered there. So in order to explicitly incorporate heterogeneity of the correlation coefficients that you meta-analyzed, there are different ways. If the moderator is categorical, then you can look at the different values of the moderator, assuming that you already identified the moderator. Then at the different values, assumably you have a homogeneous population there. Or you could actually include the product term as if it's a variable in the correlation matrix. But such product term and its correlations are often unavailable from the primary study research authors. So there's another way. The second step, after you're considering the moderator values and the potential opportunity to include the product terms, is that after you consider all those moderators, and let's assume you have a normal distribution, you have a normal homogeneous sample, homogeneous population for the correlation, then you could use a method advocated by Yu et al. In 2016 to more explicitly talk about how to incorporate the variations in the correlation coefficients. So in this paper, Yu and her co-authors were using simulated correlation matrices to create the posterior distribution of any coefficients or any combination of them, and giving you the credibility interval of those correlations. So in terms of time, we'll not be going through the steps. There are different steps involved in this simulation procedure. One key thing to note is that when you simulate, there's a possibility that you have non-positively definite correlation matrices. So you will just discard those matrices and then continue the simulation. So in the end, you will have a k minus j runs, and the j means like the number of matrices that are not positively definite. Then based upon those so many runs, and you can create the 80% credibility interval based upon any point estimate that you are interested in. However, this approach is still a pairwise approach, because each of the standard deviation of the row is considered independent of the other standard deviations. So that's one weakness continued from the previous usage of the MASEM approach. So using this method from Yu et al., you can obtain the 80% confidence interval for the mediation effect, credibility interval, 80% credibility interval for the difference, or even obtain the credibility interval for any ratios that or nonlinear combinations of those coefficients. With that said, although despite the advances of the Yu et al. Paper in terms of highlighting the way to incorporate heterogeneity, there is a response from researchers in terms of Chang in his in-price paper talking about the limitations as a comment to the Yu et al. Publication, talking about how actually the distribution of the model fit indexes are not so meaningful. However, the Yu et al. Approach is still useful in terms of providing researchers of the credibility interval of the coefficients. So the coefficients and the combination, linear, nonlinear, of those coefficients are still meaningful for researchers to understand and to potentially identify moderators of the whole model or on a particular path. But Chang's suggestion is we should not be looking at the distribution of the model fit indexes, such as RMSEA or CFI or TLI, those type of standard reports from SEM software. So the Yu et al. Paper was not actually the first publication to apply this heterogeneity logic. A few years ago, a similar logic was proposed by Edwards and Christian, where they emphasize the role played by the credibility interval. So they actually have a similar idea where a researcher can use a series of correlation matrices where you can replace the one cell with that particular correlation's upper versus lower boundary of the credibility interval. So basically, if you have 4 variables like we have here in the simple mediation model, then it will be 6 correlations in the matrix, and replacing each cell by its lower bound and upper bound, that will be 12 different matrices to fit. And then you can summarize how the path coefficients, mediation effects, or model fit indexes will be distributed across the 12 different matrices, and also assuming that they are all positively definite. So that's the first approach. As you can see, there is still a pairwise logic there, even for the Edwards and Christian method, because when you change a particular cell with its lower or upper boundaries, you still assume that cell is independent from other cells. And that weakness has been addressed by the second approach, which was proposed by Chang and Chen in 2005, 2009. It's called the two-stage SEM approach. So let's look at how data is used in this type of situation. Let's assume that we're still interested in the 4-variable mediation model. And you can actually accumulate the studies and use their correlation matrices directly. Let's assume that you have 4 studies, and some studies, like study 1, only have 3 variables available in the matrix. Study 2, you are missing X. Study 3, you are missing M1, and study 4 is missing M2. So that's not a problem. So you basically can create matrices with those missing correlations and directly estimate across the 4. That's just an example. You may have 40 or 100 matrices in order to get the first step. And there are 2 steps here, according to Chang. So first, you test the homogeneity of correlations and calculate the pooled correlation matrix. And then at the same time, because you have the raw data for each of the matrices, you can actually get a asymptotic covariance matrix in terms of showing how those correlations covary across the 440 or 400 studies. And using, because this is so-called ACOV matrix, the asymptotic covariance matrix. So this is the new element here, which is only available when you have the matrices as raw input, rather than looking at a particular correlation value as the input. Then the second step, you will use the pooled correlation matrix, which is basically the mean, the average, and this asymptotic covariance matrix as the input to calculate the SEM model using a asymptotically distribution-free method. So with this method, as you see here, you need more information. So one thing to highlight is some researchers claim that in order to use the two-stage SEM approach, you need to have one particular study that covers all the variables. So basically, you need to have one complete matrix in order to use it. According to the in-press paper by Mike Chang, that's not actually a requirement. So basically, let's assume you only have 4 studies, and you could have none of those 4 studies have a complete matrix to start with. So in this approach, the asymptotic covariance matrix takes into consideration the second-order sampling error. However, heterogeneity was only reflected in the asymptotic covariance matrix. If you want to more explicitly incorporate heterogeneity, you could actually use the Yu et al. Method. But this time, instead of creating simulated correlations from the SD of rows, this time the asymptotic covariance matrix can actually provide you with more information on that. So you can actually directly use those asymptotic covariance matrix in your simulation process, and then you can create the matrices and then run the similar procedures that Yu et al. Has suggested to get the credibility intervals of any combination of coefficients you are interested in. Just remember, the distribution of the model fit indexes will not be that meaningful. So what does this mean for us in terms of study robustness and empirical findings? There are actually a recent paper by ORM, by D. Simon and et al. They are looking at, they provide an update of a previous study looking at how people are using meta-analysis results. Their findings are similar to the previous study, where when researchers are citing a meta-analysis, they only cite about whether a relationship exists. They tend to discard information, the rich information associated with the standard deviation of rho and the credibility intervals associated with that finding. Many of the papers that are citing meta-analysis before are not even mentioning moderators or potential subpopulations as a way to guide their theoretical building and hypothesis testing. So that shows there is a gap between what information meta-analysis provides us and how how researchers are using it. So in order to better use it, we need to be aware that heterogeneity in those effect sizes reported in meta-analysis may reflect theoretically sound moderators, which means there is potentially a research question about general reliability. So whether a different setting, different subpopulation may give you different results. And after considering that, when you look at a homogeneous population, you have to remember that there may still variations even from findings of that homogeneous population. And this is pertaining to the replicability of those primary study findings. So my hope is we can all keep meta-analysis, the bivariate correlation-based meta-analysis in our mind, and also the MASEM approach in your toolbox, so that we can evaluate the robustness of any primary studies that we encounter, and keep that in mind in terms of how to accurately interpreting those findings by highlighting the potential heterogeneity and the moderators identified in those meta-analyses. And that's my hope in terms of how we can use meta-analysis for enhancing our understanding of study robustness. So again, we today are talking about the conventional meta-analysis, which is different from the so-called one-paper meta-analysis where you do an internal one on the same paper. So here I listed a few references for you if you're interested in. 2 slides here, which may give you some food for thoughts in terms of your own research for future advancement directions. Okay, thank you very much. That was my presentation.